Welcome to everybody to Investigation 2.2. This is the distributive property. So the distributive property you've already learned in 7th grade, and it was a fairly basic way to learn it, which is awesome. But today we are going to turn the distributive property up a couple notches. We're going to increase the volume a bit. So our focus question for this investigation is, how does the distributive property I meant to actually have something underlined. Distributive property apply to quadratic expressions. So, very first thing we need to think about quadratic expressions, and we're going to add a little bit of sort of vocabulary to our belt. If we look at quadratic expressions, they are essentially it's an equation without a equal sign, so it's essentially just a statement without, it's like a sentence without a period, so it's just a statement, but it has that x squared factor somewhere within it, and that is the highest power of term we will see. So we're going to understand what term means. And when it comes to a quadratic expression, the highest power that we will see is an x squared. So we'll see quadratic expressions that look like this, perhaps. We might see quadratic expressions that look like this. And we might see quadratic expressions that just simply have x squared. Regardless, everything that all of these have in common is that x squared term. And when it comes to powers, that's the highest power we will ever see when we look at quadratic expressions. So let's add a couple of words to our words worth knowing. Very first word is factored form. So when we're looking at quadratic expressions, there's a few ways we can write them. One way is something like this, where we have our x out in front and we have x plus 3. When we were creating those equations for length and area, we were looking at area would equal the length of something times the length not the length, but 30 minus the length. So we would say this is our width, and we figured out our width based on our perimeter, and we'd have length versus width. And so if we were to actually factor out this equation using the distributive property, which we will learn how to do, we would get 30 times L minus L squared. And so that L squared is telling us that it is a quadratic equation, and we have our highest exponent of being 2. But factored form is this form, where we have two statements multiplying each other. So we have L being one simple statement, that is simply the length, and 30 minus L being the width. And those two statements multiplied together get us the area. But without doing any math and just leaving it with parentheses, that is what's called factored form. Now there's also another form of factor form that you'll eventually see that looks like x plus 3 times maybe x plus 1. So we have two sets of parentheses that sum up this factored form. So maybe this is our length and this is our width, and we don't know something within our length and our width. So another way that we can write this is expanded form, and our expanded form is our next word worth knowing, and that's this format. So we had one format being length times 30 minus length in parentheses. Well, our expanded form is after using the distributive property. So after we distribute this L that was multiplying both the 30 and the negative L, we get 30L minus minus L squared. That is the expanded form of the previous factored form of the quadratic expression. I just used 3 vocab words in one sentence. That was amazing. Our next vocab term is distributive property. The distributive property essentially tells us that we have in the past played around with maybe the 7th grade version of it, saying like, what if I had 2 and I multiplied it times 1 plus 3? Well, we know that we could either write this as 2 times the stuff that's within the parentheses and get 8, or we could also say, well, we could say 2 times 1 plus 2 times 3 would get me the same thing, and we'd say 2 times 1 equals 2 and 2 times 3 equals 6, so therefore 8. So the distributive property is this second format where I'm distributing the 2 and multiplying it by one of the terms within my equation, and I distribute it to the other term as well and multiply it there. And so I'm doing it as well. So the distributive property looks potentially something like this. If I had a square and a little attached rectangle and I said this square is x wide, oh no, I'm going to say this square is maybe a wide. And this bottom part of the square is b wide plus c wide. So I could say we have a times b plus c. Well, we could rewrite this as saying, I could also say this is a times b, this little bit, plus a times c, and get the same answer. So these are equivalent expressions. Now, we could also say that we have terms within this. If I were to actually do that math, we have terms, and our terms are multiplication, division, or single variables that add or subtract. Potentially. They could also just be standing on their own. But a term would be this a times b. That is one term because a times b is our multiplication statement, and it is being added to another term, a times c. Another way we could also say this, we have this other statement up here where we have 2 times 1. So here's one term. 2 times 1 is one term. And then we have 2 times 3, which is another term. And eventually they get us one single term of 8. So they could also just be single numbers. The last one is like terms, and that kind of refers back to what we were doing with this sort of thing right here. Like terms are when we can add something together. So if we had a statement that said 2x plus 3x plus 4, 2x and 3x are like terms, so therefore I could add them. I have 2x's and 3x's, so therefore I have 5x's, and I'm adding 4 to them. So 4 is an unlike term. It is something different. So when I see like terms, I often will identify a certain term. I'll identify the terms that have the same variable to the same power. So what I mean by that, in order to add like terms, I would have to say I have x squared plus 2x squared plus x. My like terms within this statement are just the x squared and the 2x squared. Those are like terms because they have the same base in here and the same exponent. So those can be added together. I have 1x squared here and I have 2x squared here, so therefore I have 3x squared out of all of this. And afterwards, I also just simply have 1x being added to it. So like terms can become quite complicated if you're not paying attention to the exponents that are added onto those. So using all of these concepts of vocabulary words, we are going to utilize our awesome distributive property. So in 7th grade, you played around with the distributive property, and we've already kind of done a similar problem like this, but you played around with the distributive property and you essentially said, or you could either write this expression 3 times 4 plus 2, and you could either write it as saying, well, I'm going to do my 4 plus 2 first, so I have 3 times 6, and from there I get 18, or I could say I need to multiply 3 times 4, so 3 times 4 plus a multiplication of 3 times 2, and I get 3 times 2, and I will get the exact same answer, because when you multiply something, you're multiplying each term individually, or you add the terms together and then you multiply. Either one, multiplication and addition, will always end up with the same answer. So 3 times 4 will end up with a grand total of 12, and 3 times 2 will add 6 to that, so 12 plus 2 equals 18, and yet again get the same answer. So using the concept of the distributive property, essentially using this sort of rainbow method and going into this concept, we're going to use that with what's called binomials. So situations that describe areas. All right, so to start out with, looking at this, we have what's called a rectangle model. And in this rectangle model, we can describe area. So we have one area that is an area of x plus 3, and we have another one side length that's x plus 3, and we have another side length that's x plus 1. So if I were to figure out the area of this large square right here, I'd have to pay attention to one side length and the other side length. So I have x times x, which ends up giving me x squared. If I wanted to look at this side length that's off to the right of that large square, I'd have to pay attention to this x here and this 3 here, so I get 3x. As well, I could also figure out this rectangle here, and I'd look at this x and multiply it by this 1, so we'd get 1x. And very last, we would have 1 times 3 for this tiny little rectangle. So if I were to describe the entire area, I could add all of those individual pieces up and combine like terms and have my final equation for this area. So to start out with, I'm going to start out with my largest degree polynomial term, which would be x squared. I would then go to one of my next smallest, which is 3 times x. Then I'd add on my next smallest, which is 1 times x. And in all reality, these are the same degree polynomial, or the same degree terms. So they would add together eventually, but they are not smaller, necessarily bigger than each other. And then the very last, we have 1 times 3 to represent our smallest rectangle. So after this, we can continue to describe this equation. We could say we are done. However, any mathematician would then tell you, no, you're not, because you have not found like terms. You have not simplified. You essentially haven't taken that equation, or that fraction of 4 over 2, or 2 over 4, down to 1/2. You need to take it to its most simplified version for it to be completely correct. So we're going to do that same thing, and the way we do that is we need to simplify our terms. So we have our x squared that still remains there, and we have 3x plus 1x. So how many total x's do we have? We have 4 x's. And very, very last, we have 1 times 3, which is 3. So this equation right here describes the area of this awesome rectangle. So it's kind of interesting. If I wanted to, I could describe what I just did. If I look at what I just did here, I distributed the terms for various areas. I then combined like terms, and I finally found my simplified answer. So there is where I'm done. Now we're going to take this one more step, and I'm going to give you one more method that you can use. And this only works for what's called multiplying two binomials. So what we have here is two binomials. We have two terms, therefore bi means two, and nomial means term. So we have two binomials. Kind of fun. So we have two binomials, so two term expressions, and we can use what's called the FOIL method. And the FOIL method is kind of cool. It's a simple way to go about multiplying binomials. And if you ever have a binomial times a trinomial, which we'll find out later, you could also use this method, but actually expand it a couple more steps. So to start out with, we have F. F within the FOIL method stands for first. First is in first terms. Our first terms are this x and this x at the very beginning. Essentially, they are the first terms in each set of parentheses. And we're going to do a little multiplication. So we have x times x. Then we're going to do O, which means outside terms. Outside terms refer to the two terms that are on the outside, the x and the 3. So we could say plus x times 3. And I'm saying plus x because we have these pluses in here, so everything's going to be added. And this is positive and this is positive, so it's going to remain positive in the middle. Then we go on to our I term, which is inside. So our inside terms are the ones that are kind of touching each other next to the parentheses. So we have plus 1 times x, and then L stands for last terms. And so we'll take our last terms in each of these situations, or 1 times 3. So from here we can simplify all of this. We have x times x, which equals x squared. When we have x times itself, we'll get x squared. When we have x times 3, we could rewrite that as 3x. If we have 1 times x, we have plus 1x. And very last, 1 times 3 equals 3. So the last little step we need to take is we need to say 3x plus 1x gets me 4x. So I'm now simplifying my like terms. And I get x squared plus 4x plus 3. So this FOIL method can be incredibly helpful with various problems. Now we're going to go through the same method with 2 more problems to practice it. So this method, if you notice here, we ended up getting the exact same answer as we did here with our area equation. So you can essentially find the area of a rectangle in 2 different ways now. Let's try 2 practice problems and then I'll let you go. So here's a practice problem. We have x minus 7 times x plus 2. We are going to use the FOIL method. So first things first, we're going to multiply our first term. So we have x times x. We're then going to multiply our outside terms. So we get plus x times 2. We're then going to multiply our inside terms. So we have plus a negative 7 times x. And we'll multiply our inside terms, outside terms. And we get plus a negative 7 times 2. Do a little bit of math. X times x equals x squared. Negative 7 times 2 gives me negative 14. And our middle stuff that we have here, we have x plus 2 times, 2x minus 7x. So we need to do a little addition in there. So if we do that, we get x squared minus 5x, 2 plus a negative 7 equals negative 5, minus 14. And so that is our expanded form. If we want to talk about that, that is our expanded form of our previous factored form of an equation. Our next one that we have is this. Actually, I guess we have two more after this. We have x plus 2 squared. Now, we know with squaring things, we essentially are saying, well, I have x plus 2 times itself, x plus 2. So I wrote them in two different colors so that way we could see them, but really we're just multiplying it by itself. So FOIL method tells us we multiply our first terms first. So we have x times x. We then multiply our outside terms next. So we get plus x times 2. Then we multiply our inside terms. So we get, again, plus 2 times x. And then we multiply our last terms, or plus 2 times 2. Let's now simplify things. So x times x equals x squared. 2 times 2 equals 4, and if we wanted to, we could totally do this right away. We have x times 2 plus 2 times x, or 2x plus 2x. We can rearrange however we see fit because it's multiplication. So we can say that's now 4x. So there's our expanded form of our previously factored equation. Very last one is sort of getting us into what we're going to do tomorrow, which is looking at different cases, and this is specifically the difference of squares. Difference of squares can follow a special rule, and you'll notice what that is after we do a couple of these problems tomorrow. But it deals with having the same first term and last term for both equations, but opposite operations within those. So if we were to do the math, we have x times x. Then we have outside terms, so we have a negative 5 times x. Then our inside terms, which will have a 5 times x. And we will have our outside terms, and we'll have a positive 5 times a negative 5. So doing the math, we get x times x, which is x squared. We then get negative 5x plus a positive 5x, and a negative plus a positive, if you were adding those together, we'd get 0x, which that would mean this whole term just disappears. And we have 5 times a negative 5, which gets me a negative 25. So my final answer would be x squared minus 25. So if I looked at here and looked back at what we have going on, 5 times 5 equals 25, and I have a negative here, so it follows this operation sign, and very last I have my x squared. It's getting a little bit deep, however, you'll figure out more tomorrow. I hope you followed along with this distributive property. If you need to, watch the video again, but I hope this helps with your homework and the investigation. Enjoy.